Okay, so welcome to the lecture of the subject Signal and Systems. In this lecture, we will discuss the topic linear time invariant systems. There are various properties of any systems such as linearity, time invariance, stability, causality, invertibility. Out of all these properties, the most important two properties are linearity and time invariance, and in this lecture we will see how, if a system is linear and time invariant simultaneously, what is its importance and how analysis can be performed on such systems is what this lecture is about. So firstly, in this lecture we will establish what is linearity. Linearity is basically for any system, if xt corresponds to input and yt corresponds to the output, and similarly for a discrete time system, xn is the input and corresponding output is yn. So this arrow represents if the input is xn, the output is yn. So if it is so, linearity consists of two components. The first component is that of scaling, which means that if the input is multiplied by any constant, a scalar quantity, then the output is multiplied by the same constant, and this property is called scaling, also called homogeneity. Secondly, linearity also satisfies what is called superposition. The superposition is that if x1 of t produces y1 of t, and if x2 of t produces y2 of t, then in that case the superposition of the inputs, that is to say input x1 combined with x2 will generate y1 plus y2. If for any system the two properties, scaling and superpositions, are satisfied simultaneously, the system is said to be linear. That's the first definition. Secondly, for LTI system, the time invariance part. By time invariance we mean that the system is invariant to shift at the input, which means to say that if x of t produces y of t, if x of t produces y of t, then the shift at the input produces the same shift at the output. And this is what is meant when we say that it is time invariant system. It is time invariant, which means that a shift in the time at the input corresponds to the same shift at the output, and therefore system becomes time invariance. Now if both these properties are simultaneously satisfied, the system is said to be linear time invariant systems. Linear time invariant systems. As far as some input relations, to just understand these properties that I have said, it can easily be proved, not the part of this lecture, but it can easily be proved that if yt is equal to m times of xt, you can understand the shift that will be caused at the input will correspond to the same shift at the output, and therefore the system is time invariant. Since it is only multiplying the input by a constant m, the system is said to be linear also. So this is an example of linear time invariant systems, can be proved. Similarly, the second, the shift will be invariant, but due to the inclusion of c, the system is non-linear. It is time invariant, but it is non-linear. Similarly, if we look at the third system, here x of t corresponds to yt, so the linearity will remain, but due to the presence of this t, the shift at xt, t minus t naught, will not give y of t minus t naught. So this can be proved that this is linear, but it is time varying rather. It is not time invariant, it is time varying. The fourth, yt is equal to x of sin t, is by default linear time invariant, and it can be proved as well that the shift at input will correspond to the same shift, and superposition and scaling will give the same output. Finally, x square of n is like, first of all, this is a discrete time system equation. The yn is the discrete time output. The output is squared. The shift will remain, but the system becomes non-linear. The system becomes non-linear. It is time invariant but non-linear. So in this lecture we are basically concentrating on linear time invariant systems and why it is important. Now when it comes to the importance of linear time invariant systems, we come to the concept of what is called impulse response of the system, the concept of impulse response of the system. So if first of all, for a discrete time systems, this what we are discussing is for discrete time systems, then x of n gives an output yn, then the impulse response of the system is defined as, for the system, if the input is impulse signal, the output is said to be the impulse response of the system, the response of the system to the impulse signals. Delta of n, as we know, is 1 when n is equal to 0, it is 0 when n is not equal to 0. So this is basically Kroneker's delta, it is called. It is a discrete time delta signal. If the discrete time delta signal is provided at the input, the output is said to be the impulse response of the system. As I already said, it is the response of the system to the impulse signal. Similarly, there is also one quantity which can be used for LTI systems, is said to be the step response of the systems. So second signal that is important is the unit step signal, and unit step signal is u of n. So when the input is unit step signal, the output is said to be step response of the system. The output is said to be the step response of the systems. Now for continuous time systems, the same definitions also exist. So the impulse response of the continuous time system will be defined as, when the continuous time input signal is the unit impulse signal, which is called direct delta signal, then the corresponding output is said to be impulse response of the system. H of t is called the impulse response of the system. Similarly, for continuous time systems, there is also what is called the step response of the system. The step response of the system is defined that when the input is unit step signal, as we know, the definition of ut will be that it will be 1 when t is greater than or equal to 0, it will be 0 when t is less than 0, which means to say a signal of this form. U of t will be a signal of this form. So if a signal is like this, then the output is said to be S of t. Of course, the unit impulse signal and unit step signal are interrelated. So the basic relationship, as we are aware of, is that the impulse signal, the impulse is first order derivative of the step, or we can say that the ut can be derived from integration of delta t. If impulse gives the impulse response and a step gives the step response, the same relationship again becomes, and that is that h of t is d by dt of st. So if I have the step response, I can just differentiate it with respect to time. For one time, I will get the impulse response of the system, and subsequently, if I have h of tau, which means to say if I have impulse response, I can just integrate it, the inverse system of differentiation, I can get the step response. So this is how step response and impulse response are interrelated. Now, just a quick example. If I have a impulse response of the system, first of all, always look that it is corresponding to time t, which means to say it is a continuous time system's impulse response. So this is the response of the system. Response means output of the system when the input is delta of t. If it is so, what will be the st? So as I have discussed in the previous slide, st is nothing else but the integration of impulse response. So I will write h of tau, which means to say I will replace this t with tau here, which means this will become e a tau and this will become u of tau. So I will write this, and I will use the property of unit step signal, that u of tau will be 1 when tau is greater than equal to 0, or u of tau will be 0 when tau is less than 0. If it is so, I can use this one in the limits, which means to say this minus infinity to 0, we have 0. This means what? This means from minus infinity to 0, there is nothing. It is 0. So what I can do, I can change this minus infinity to 0, the lower limit. The upper limit as per the definition remains t, and I can integrate e raised to the power minus a tau. The integration of e raised to the power minus a tau will be e raised to the power minus a tau by a tau, and I will put the limits 0 and t. I will put the limits, the lower limit is 0, the upper limit is t. So, corresponding step response, the corresponding step response is 1 minus e raised to the power minus a t ut. Understand this, since we are starting the integration at 0 and to t, this ut comes. It just signifies that if t is less than 0, the step response is basically 0. The step response is basically 0 if t is less than 0. Ut just signifies that. Now, if we have the step response, we can go back and derive the impulse response, because we said and stated that the two are interrelated. The integration of impulse response is step response, the differentiation of a step response will be the impulse response. So, we will verify this. We will verify this result from this example, because we have by our choice taken the impulse response, and therefore we can just differentiate the step response and get back the original impulse response that we have taken in this lecture. So, h of t is d by dt of st. Okay. So, in this case, the st that we have derived is 1 minus e raised to the power minus at into ut. I will differentiate it with respect to time. Now, the first part is constant, you can understand. The second part is a composition of two signals, which means to say I can write this ut and minus something u into v. So, these are two functions. So, if I differentiate multiplication of product of two functions with respect to the independent variable, I have the differentiation of first function and the second function remains constant, plus the differentiation of second function and the first part remains constant. So, that is what we will do. The impulse response will be d by dt of this and keep this as constant, the second function. Second part will differentiate the second function first and leave the first function as it is. Now, the differentiation is very easy, because this portion is simply the constant. So, differentiation will be 0. This portion will give me minus will come outside. So, it will become e raised to the power minus at ut, and there is also 1 by a from the previous slide. So, that cancels out, and I have e raised to the power minus at ut. The second part is the derivative of ut, which is delta t. The derivative of unit step signal is impulse signal. So, I have delta t multiplied by this u, the first signal. Now, this delta t only exists at t is equal to 0, and if I put t is equal to 0 here, this will become 1, because it is e raised to the power 0, and this eventually becomes 1 minus 1, 0. So, second part becomes 0, which means to say the impulse response is e raised to the power minus at ut, which we selected in the previous slide. So, the original question was that what is the st when ht e to power minus at ut. So, we calculated st, we differentiated st to verify the ht, and the two are interrelated. Now, in all of the signal system analysis, it is generally of importance that we can derive what is the impulse response of the system and step response of the system, which we have discussed here. Now, we will move forward that why these two, and particularly why h of t is important. Why h of t is important? The h of t is important because of convolution operation, and convolution will be just to differentiate, it will be divided in two parts. First will be for discrete time systems, and second will be for continuous time systems. For discrete time systems, we will say that it is convolution sum. So, this sum written here just signifies that we are currently talking in terms of discrete time systems. Discrete time systems. So, we are talking in terms of LTI systems. A linear time invariant system can be characterized only with the help of impulse response, which is h of n. H of n, remember, is the output of the system when the input is delta of n. That is definition. So, we will establish what is convolution sum for discrete time systems. If I have a system S, I apply delta of n, which is the impulse signal. By definition, the output is impulse response h of n. System is linear time invariant, and remember linear time invariant systems for discrete time systems are also called linear shift invariant systems. They are also called linear shift invariant systems, LSI systems. So this means to say that time shifting will be applicable. So if the system is LSI system, I shift the input by minus k, the output will also be shifted by minus k. That's the theory. Similarly, this will be a linear system. Linearity consists of two things, scaling and superposition. So scaling also satisfies here, which means to say if the system at the input is multiplied by a constant, the output shall also be multiplied by the same constant because of the property of scaling. Because of the property of scaling, it will also be multiplied by the same amount. And finally, superposition must satisfy, which means to say if I add these components at the input, the output shall also be additions of all the individual outputs. So individual output is this. If I add for all values of k at the input, the output will also be added version of all the individual outputs. This portion is called superposition. So by superposition we mean that if I add from k minus infinity to plus infinity x of k delta n minus k, the output will be k minus infinity to plus infinity x of k h of n minus k. Now we should look at the last point again separately. What is at the input? The input is summation k from minus infinity to plus infinity xk delta n minus k. Remember, this delta n minus k is the impulse signal. It is delta of n minus k is basically, it is equal to 1 only when n is equal to k, or clearly we should write k is equal to n, because the variable of summation is k, and it is 0 when k is not equal to n, and therefore there is no summation. We just put k is equal to n in the summation, and that's the output, which is x of n. So if it is so, you can see that now our definition becomes that if the input is xn, the output is summation k starting from minus infinity to plus infinity x of k h of n minus k. This is called the output of the system yn. It is a summation because it's a discrete time system, so it is summation. The variable of the summation is k. You will sum it for all the values of k. You will put the limits for k. You will get eventually a function in n. You will get a function eventually in n, and therefore you will end up getting the output. And what is the importance? The importance is that we can obtain the output to any general input if we know the output of the system to the impulse signal, because if we know the impulse response of the system, we can calculate any output. So this we look at with a very important example. Suppose there is a system in which the impulse response is a raised to the power n u of n, and the input to the system x of n is also a raised to the power n u n. So we apply the input which is equal to x of n, and we want to measure what is the corresponding output, which means to say what is xn convolution hn. We want to solve this. Now if I want to solve this, I will need the definition of convolution sum, which is basically summation in k for all values x of k and h of n minus k, isn't it? So which means to say I will write x of k. X of k can be written from x of n, because if x of n is like that, x of k becomes n replaced by k, which means to say a raised to the power k and u of k. And similarly, h of n minus k shall be can be evaluated by replacing n by n minus k. So which means to say it will be a raised to the power n minus k and u of n minus k. correct. So this is the operation. First of all, we will apply what is the convolution sum to evaluate the output. We will now replace our signals. So our signals becomes, first signal is x of k, second signal is h of n minus k, isn't it? Now we will we have to solve the summation. The summation is for the variable k, remember, and k starts from minus infinity to plus infinity. Now we will use u of k to change the limits of summation. So first of all, we know that u of k is 1 for k greater than equal to 0, and it is 0 for k less than 0. So of course the summation which starts from minus infinity shall start from 0. So the lower limit can be changed because of this uk, and therefore we can write that yn is basically k of 0 to infinity, and in place of uk we replaced it by 1. So I replaced it by 1, and remaining things are there. A raised to the power k is there, a raised to the power n minus k is there, and u of n minus k is there. Secondly, we will use this unit step signal and its properties to change the limits. So we know that u of n minus k will be 1 when this n minus k is strictly positive, 0 or greater than that. If it is so, we actually mean that n is less than or equal to k, but the variable is k, so we should decide upon k. We should decide about k. This will be greater than, and this will be smaller than n. K will be smaller than n. So basically what I am saying is that the upper limit infinity can be holded to n only. So that we will do subsequently, that u of n minus k will be 1 when k is less than or equal to n. So if the variable of summation is k, the upper limit of k can be not infinity, it can be kept to n. So that we will do that, the upper limit is changed to n, and in that case u of n minus k also becomes 1. Now you can see that bases are same, powers are added. So this is basically a raised to the power n comes out, and a raised to the power k, a raised to the power minus k remain, and this is summation of 1 from k is equal to 0 to n. This is the output. Now we should pay attention while evaluating this summation. You can use some formula also, but this is a basic computation. If we are adding 1 from 0 to n times, we are actually adding it for n plus 1 times, because 0 is also counted, and therefore the output is yn is equal to a raised to the power n plus 1. Remember, this summation is of course a finite summation, so it will converge. It is adding 1 to n times, but it is adding from 0 to n times, so which means to say we are adding it for n plus 1 times, and therefore summation is n plus 1. But the final result that we are getting is not the final result yet. We have to put the limit on n. For what values of n the system is producing this output. In order to understand that, we should go a little bit to the graphical interpretation of this thing. So while computing the graphical interpretation of this signal, first of all we will understand that the convolution took place for x of k and h of n minus k. So x of k, assuming that modulus of a is less than 1, will be a decreasing function, and it will start at 0, and at minus 1 the value will be 0 because of un. Now the second signal that is required is h of n minus k. So first of all, this will be h of minus k, and if I talk about h of n minus k, it will be something like this. This will be h of n minus k. The plotting is very straightforward. Remember, these are the two same signals. The impulse response is equal to the input signal. So what we are doing in convolution is that this is summation of xk multiplied by h of n minus k. This is multiplication. So if it is multiplication, we must see where the multiplication exists, and we must determine where the multiplication is 0 by default, which means to say that if you can see this, this is h of n minus k, and this is x of k, then when n, the variable is n, when n is behind 0, when n is behind 0, there is no overlapping. So if there is no overlapping, this product will be 0. The product is 0, the summation will be 0. Firstly, we calculate the product and then the summation. So basically what is to be understood here is that what we have calculated mathematically should also involve that the summation will only yield for positive values of n, and therefore we also need to multiply u of n to it, u of n to this. Okay. So final result should also involve what is the restriction on u of on time n. Now we can move forward and we will now discuss continuous time systems. How can we evaluate the output for continuous time systems? Here also we will use the same definition, that if there is a system and delta of tau is applied, the output is h of tau. This is impulse response definition. Then we perform scaling, shifting first of all. If we perform shifting, so delta of t minus tau minus k will give me h of t minus tau. So basically this is not k, this is tau. So which means to say that the shift is invariant in the system. Secondly, it is scaling is also applicable. So h of tau multiplied by that, x of tau multiplied by the system will also give the same result. And in this case we will use superposition, which will be integration for continuous time systems. So the output will be input multiplied by h of t minus tau. From this the definition comes, so we are looking at it. If you look at the input now, this is basically nothing else but x of t. This is x of t. If it is x of t, which means to say that the input is x of t, the output is this convolution integral, which means to say that the output to any input x of t can be evaluated by using this integration process. This is called convolution integration, which we will look at in subsequent slides. And why this LTI system is important is because to any general input we can evaluate the output of the system. Now the most interesting question for this can be when the signals are truncated. So we will look at a question in which the signals are truncated. First of all, suppose there is an xt which is a square pulse which has a magnitude of a1 which starts at 0 and goes up to 3, and suppose that there is a h of t which is of magnitude a2 and it is from 0 to 1. So these are called basically truncated signals, because at a particular value of time t both the signals are diminishing. So what will be the convolution of this signal, which means to say what will be the output, which will be minus infinity to plus infinity x of tau h of t minus tau d tau, correct? So we need to evaluate that. So x of tau is very easily gettable. We will just replace this t by tau, and that is easily available. We need to calculate what is h of t minus tau. H of t minus tau is required. So our general formula will remain this, and we will first of all calculate what is h of t minus tau. So x of tau is straightforward. X of tau will be a1 from 0 to 3, but the independent variable, remember, is now tau. H of tau is basically which was there in the question, but we'll just replace t with tau. Now what we can do, we have to evaluate h of t minus tau. Remember, the variable of integration is tau, so we'll work accordingly. So firstly, if I have to evaluate h of t minus tau, basically the variable is this, so I will firstly evaluate h of tau plus t, and variable is tau. So which means to say that the signal will be, and the independent variable of the signal will be tau. This portion which is at 0 will become minus t, because this is tau plus t is equal to 0, which means to say tau is equal to minus t. Tau is equal to minus t. Okay. and this first one, this 1 which was there originally will become 1 minus t, and we are only at tau minus t. Remember, we require h of t minus tau. We remember h of t minus tau. So if I do that, and remember the variable is tau again, so the variable is tau, the points will just switch over. The points will switch over, and in that case it will become, first of all, t minus 1, which is minus 1 to t. You can just say that this minus t, 1 minus t will be multiplied by minus 1. So it will come here to become t minus 1. Similarly, this minus t will be multiplied by minus 1. In this side, it will become t. So now both these signals can be understood. Firstly, we have x of tau. Secondly, we have h of t minus tau, and now we start to evaluate the convolution. We start to evaluate the convolution. Very slowly we will do that because it is a concept that requires attention. We, in order to evaluate this, we must understand what is that we need to do. We need to evaluate the integral. Here we want the product of x of tau and h of t minus tau. The variable of integration is tau. So we firstly want what is the product, then we will integrate accordingly for the values of t. So now if we consider the first case, that is to say that t is less than 0. So if t is less than 0, then in that case you can understand this point q, which is t, is less than 0. Less than 0 means if it is 0, this plot is something like this, that this is a2 and it is t minus 1 and this is t, and this t leaves behind 0. So if t is less than 0, there is no overlapping. There is no overlapping. So if there is no overlapping, you can see that yt is 0 for the case when t is less than 0. Very straightforward. This first the first one can be evaluated. Okay. Second, we will now proceed. So we will just maneuver this q one by one. Second is that x of tau is there between 0 and 3. H of t minus tau now shifts to the right. We will go from minus infinity to plus infinity. So it is moving outside, and we will now select the limits. Now look how the limits are selected. Firstly, the product we will plot, but before that, how the limits are selected. The operation remains the same, x of tau, h of t minus tau, d tau, and this product is what we are interested in, but also the limits. The limit is for t, and understand this, that this complete width is 1. This complete width is 1, and this width is 3, which means to say that the second pulse which is there is of smaller width. So we will select the values of t according to which the limits of the integration changes. We will just look at the limits of the integration. So in order to do that, we just move forward. Firstly, we will say that this point q comes outside 0. The q comes here, the magnitude is 2. The q comes here, but the point p remains behind t equal to 0. The point p remains behind tau is equal to 0. And in that case, you can understand that from the plot, if I have to evaluate this integral, since this signal starts at 0 only, the overlapping is this. The overlapping is this, and if this is the overlapping, you can understand that the integration will start at tau is equal to 0, because the independent variable of integration is tau. So integration will start at 0, and maximum it can go to t. Maximum it can go to t. So if it maximum goes to t, you can understand that basically this multiplication is nothing. The multiplication I have kept very simple. It is constant multiplied by constant, which will remain to be constant. So basically it is a1 a2 d tau from 0 to t, but the limit is what is important. So for this thing, and you can understand that the second portion it says that t is less than 1. So t is greater than 0, but it is less than 1. If it is so, the output will be 0 to t a1 into a2 d tau. So that integration is very simple. D tau will give you tau, the limits are from 0 to t. So I will eventually get a1 into a2 t for t ranging between 0 to 1. For t ranging between 0 to 1, this is what we will get. Now we will move forward. So we will take the q point more forward. Again the x of tau remains the same from 0 to 3, the magnitude is a1. We can now take h of t minus tau, which is now again moving towards the right side. So in that case, what we are going to take is that the point q has come outside it, but the total width is 1. The total width is 1. So if I take this integral, and if I want to check when does the limit changes, I will take that the p is now ahead of 0. This is tau is equal to 0. So I am assuming now that the p is right of tau is equal to 0. The q is just one unit ahead of p. So if I look at that, which means to say that t minus 1 is now, this is to say that p is greater than 0 in tau. So t minus 1 is greater than 0 and q is behind 3. And q is behind 3. So if that happens and I evaluate the integration, you can understand the lower limit will be from t minus 1 and the upper limit will be t, because this is the overlapping, isn't it? The overlapping is this only, the complete thing will be overlapping. So the lower limit will be t minus 1, it is varying, and the upper limit will be t. The integration will be for 1 unit. Remember, from t to t minus 1, the unit, the gap is 1. And x of tau into h of t minus tau, both of them are constants. So basically t1 minus t to t a1 a2 d tau. So if I integrate that, the integration is nothing. But accordingly, if t is between 1 to 3, there is a equality sign at 1 and it is approaching 3, then the output of the system is a1 a2. Then the output of the system is a1 into a2, and that means that now the point q is behind 3, but p point is ahead of 0. We move forward to the right, h of tau. So again x of tau remains like this, 0 to 3, the magnitude is a1. H of t minus tau is this, which in case we are again moving forward. We now look at the next thing, that is that the point q is ahead of 3. The point q is ahead of 3, and remember the point q is basically t. The point q is ahead of t, but this 1 minus t is basically, which is to say t minus 1 is behind 3. So if I evaluate this, the product is the overlapping is this. The overlapping is this, and you can understand the limit is changing. The lower limit will be t minus 1. In the previous case also the lower limit was t minus 1, but in this case the upper limit will not be t, because the integration is only up to 3. So which means to say that it is from t minus 1 to 3. The integration this time will be from t minus 1 to 3. So if I evaluate this integral, this will be a1 into a2. This magnitude is a2 basically. So the product is a1 into a2, and from lower limit 1 minus t to 3, if I evaluate, it will be 4 minus t, a1 into a2, and this is from 3 to 4. What happens when 3 to 4? Now you can very easily understand that when t minus 1 moves ahead of 3, what happens? So if my x of tau is this, my h of tau is this, and if I am now saying that this t minus 1 is ahead of basically 3, then in that case we mean to say that basically this means to say that t is greater than or equal to 4. So if that is so, yt will be basically, you can see, 0. There is no overlapping. On this first signal remains to the left side, second signal the shifted version to the right side. So truncated versions are not getting multiplied, and therefore we don't have any overlapping, therefore yt is equal to 0. So if I summarize the results, if t is less than 0, the output is 0. If t is between 0 to 1, the output is a1 into t. If the t is between 1 and 3, the output is a1 into. If it is between 3 and 4, the output is a1 into 4 minus t. If t exceeds 4, there is no overlapping, and then there is no output of the system. So for truncated systems, we have to pay a little bit more attention. However, for non-truncated signals like this, we can directly evaluate the convolution. But this is also a unique case in itself. So first of all, I have two signals. Remember, the output y of t will be integral minus infinity to plus infinity x of tau h of t minus tau d tau, correct? So we need basically x of tau and h of tau. X of tau you can understand is straightforward, e raised to the power 2 tau u of minus tau, and because of u of minus tau, it will exist for tau less than equal to 0. And if I put negative values of tau in e raised to the power 2 tau, you can understand that it will decrease in this direction. So first of all, it will be towards negative infinity, and it will be something like this. Okay, it will be something like this, not this. This will be e raised to the power 2 tau u of minus tau, correct? Second signal is h of t minus tau. So what will be my h of t minus tau? You can understand h of t minus tau is basically, I will write it u of t minus tau minus 3, which eventually means that u of minus tau plus t minus 3. So if I want to plot this signal, it is going to be slightly easy. First of all, I will plot u of tau plus t minus 3. So if I plot this only, the axis is tau, suppose the axis is tau. If I want to plot this, this is tau greater than equal to minus times of t minus 3, isn't it? So not going into what is t positive or negative, this is a right sided signal, t minus 3 to the right. This is h of tau plus t minus 3, but we are not interested in this. We are actually interested in h of t minus tau minus 3, isn't it? So we require an inversion. So inversion of this signal, you can understand, this will go towards this and it will become a left sided signal. So very easily it will be something like this. This point will become negative times. So if it was minus times of t minus 3, it will become t minus 3, and this signal was left sided, decreasing signal. So e raised to the power 2 tau u of minus tau is this, isn't it? So these are my two signals. The magnitude of this signal is 1, and I want to compute the convolution of this signal. So how can I evaluate the convolution? The convolution yt will be minus infinity to plus infinity x of tau h of t minus tau d tau, isn't it? So we'll select the values of t, and in order to do that, you can understand the limits of the integration will change based on whether t minus 3 is to the right of this or to the left of it. So if t minus 3 is to the left of 0, so this point is here, then you can understand that this shall remain like this. The integration will remain like this, because it will be multiplied by like this up to t minus 3. So which means to say that area will be something like this. The overlapped area will be something like this. So if I evaluate the signals, the limit, lower limit will be minus infinity, the upper limit will remain t minus 3, and the function is e raised to the power 2 tau and d tau, because u of t minus tau becomes 1. So it is very straightforward. I can just the integration will be e raised to the power minus 2 tau divided by 2 tau, and I will put minus infinity and t minus 3. So therefore the yt, not going in any mathematics, I can just replace not tau, so it will be 2 only. So I can write e raised to the power minus 2 into t minus 3 divided by 2 for the case when t minus 3 is to the left of 0, which means to say t is less than 3. T is less than 3. If t is less than 3, I will have this. Secondly, the case when this signal is to the left, but the t minus 3 now crosses 0. So in that case, the overlapping, you can understand, if I plot the overlapping, since this signal is to the left and this signal is even here, the overlapping is only this. So which means to say it will start at 0 and move towards minus infinity. So if I evaluate now y of t which is minus infinity to plus infinity x of tau h of t minus tau d tau, then in that case I can surely write that it is from minus infinity to 0 only. The overlapping is still 0. It is t minus 3, but the product does not exist, and the product is e raised to the power 2 tau d tau, which means to say it is e raised to the power 2 tau by 2 from minus infinity to 0. So if I put the upper limit, I will get 1 by 2 basically. The lower limit tends to infinity. So y of t will be 1 by 2 for the case that t minus 3 is greater than 0, which means to say t is greater than equal to 3. So I have just two different zones of this. So we can evaluate in this manner convolution to any kind of signals. In this case, we have seen for the signals which are unbounded. So u of minus t means it is starting from minus infinity, and t minus 3 is from 3 towards right. So if I form the convolution, I can get the corresponding output. Similarly, I can calculate the output to truncated signals also. So we have in this lecture introduced what are linear time invariant systems, and what is the concept of impulse response, and how impulse response can be used to evaluate the output of LTI systems to any input systems. Thank you.